Good morning, students. Today we are going to discuss about the reciprocating masses, that is balancing of reciprocating masses. In the last class, what is meant by reciprocating masses and how the reciprocating masses will be balanced, and what is the primary force and what is the secondary forces, and how to make the balancing. Then here, so finally what we have get it in the last class, that is the resultant unbalanced force at any instant is m omega square r into square root of 1 minus c square into cos square theta plus c square sin square theta. If the balancing mass is required to be balanced, then revolving masses as well as reciprocating masses will be BB, that is balanced mass, into the radius of rotation of the balanced mass, that is small b, that is capital B, mass of the balanced mass into radius of rotation of the balanced mass, that is small b. Capital B into small b is equals to m1 plus cm into r, where m1 be the magnitude of the revolving masses and small m be the magnitude of the reciprocating masses. This is the final result what we have received in the last class. Then in the today's class, we have to solve some nominal problem. Then how to solve the problem that we will discuss here. A single cylinder reciprocating engine has a speed of 240 rpm and the stroke 300 mm, and the mass of the reciprocating parts 50 kg and mass of revolving parts is 150 mm, radius is 37 kg. So from the given data, what we have to note down the n is equals to 240 rpm and omega is equals to 2 pi n by 60, so 25.14 radians per second. Then stroke is 300 mm and mass of the reciprocating parts is 50 kg. So in the previous formula we have received that is small m be the reciprocating masses and small m1 be the magnitude of revolving masses. So here also we have to substitute small m is 50 kg and m1 is 37 kg, and the radius of rotation of the revolving parts is 150 mm, that is 0.15 meter. And what is the next thing is, if 2/3 of the reciprocating parts and all the revolving parts are to be balanced, that means 2/3 of the reciprocating parts, that is c is equals to 2/3, and find the balancing mass required at a radius of 400 mm. That means small b is given, that is radius of rotation of the balancing mass. We need to find out capital B. Okay, the balanced mass required at by radius 400 mm, that is 0.4 meters. And what is the residual unbalanced force when the crank is rotating at 360 degrees from the TDC, top dead center? So let us find the formula. So let capital B with the balancing mass to be required and small b with the radius of the rotation that has already given in the problem 400 mm, that is 0.4 meter, that is given. So finally what is the formula? This is called the formula, that is BB is equals to M1 plus CMR. So substitute in that, with that BB is equals to M1 plus CM into R. B is given, that is 0.4, small m1 that is 37 plus c 2/3 into small m, that is radius mass of the reciprocating parts, into 50 into radius of rotation 0.14. So finally mass of the balanced mass is 26.38 kg. And then secondly, residual unbalanced force. What is residual unbalanced force? So the residual unbalanced force or the speed we need to find out. For a crank angle, how much is from TDC? It is 60 degrees centigrade. So the residual unbalanced force formula is m omega square r into square root of 1 minus c whole square cos square theta plus c square sin square theta. That is already given in the last class. So this is the formula, main formula. Okay. There we substitute it 50 mass of the residual, that is reciprocating only we are taking out. So by substituting all the values we get it the final formula as 2849, that is 2849 newtons. So this is a very simpler problems we are having in the reciprocating masses. By simply remembering the formula is enough to solve the direct problems. Then next, partial balancing of locomotives. That is, actually we know that the locomotives usually having two cylinders. Why we are mentioning particularly partial balancing? No one load or masses not to be fully balanced. It is maybe possible for theoretical, but in practical there is no fully balancing of any reciprocating masses. So most of the cases for any losses we are considering only partial balancing of reciprocating masses. So here the locomotives usually have two cylinders with cranks placed at right angles to each other, and in order to have uniformity in a turning moment diagram. And then the two cylinder locomotives may be classified as inside cylinder locomotives and outside cylinder locomotives. What is the inside and what is the outside? So inside cylinder, the figure A will shows the inside cylinder, figure out B will shows the outside cylinder locomotives. Then what is the difference? That means in the inside cylinder locomotives the cylinders what we are placing, that is two cylinders are placed in between the planes of the two driving wheels. If you see in the diagram, the two driving wheels, in between these two the cranks are placed. The cranks is nothing but the attached to the cylinder only. So at the same time, the as we know in locomotives the two cylinders are right angle to each other, placed at the right angle to each other. So for cylinder 1, cylinder 2 is at an angle of 90 degrees right angle to each other. Then automatically we can guess if the outside cylinder locomotives, whereas in the outside cylinder locomotives, in the name itself outside cylinder, so the cylinders are placed outside of the driving wheels. The two driving wheels are placed outside the driving wheels, one on each side of the driving wheel. So we have to run up the first crank is rotating the left side driving wheel, and the second is turning the right side. So for one crank, one drive wheel is attached. The and again the locomotives may be single or uncoupled locomotives, or in locomotives they are of singular or unbalanced. Uncoupled, and the second is coupled locomotives. So what is a singular or uncoupled locomotives is one in which the effort is transmitted to one pair of the wheels only, whereas in coupled locomotives, that is the outside cylinders, what is the called singular or uncoupled locomotives or coupled locomotives. In the coupled locomotives the driving wheels are connected to the leading and trailing wheels by an outside coupling rod. So this is the major difference. So partial balancing of locomotives are of two types. One is inside and the outside. After that, again these locomotives are classified to singular or uncoupled and coupled. So then coming to the next, what is the effect of partial balancing of the reciprocating parts of two cylinder locomotives? We already discussed that the reciprocating parts are only partially balanced. Due to this partial balancing of reciprocating parts, there is an unbalanced primary force along with the line of stroke and also unbalanced primary force perpendicular to the line of stroke. So here we need to remember that there is an unbalanced primary force is along the line of stroke, and also the unbalanced primary force may be perpendicular to the line of stroke. This effect of unbalanced primary force along the line of stroke is to produce due to the unbalanced primary force along the line of stroke. There is a two effects will be there. One is variation in tractive force and swaying couple. So due to the unbalanced primary force along the line of stroke, it may produce variation in tractive force along the line of stroke and swaying couple. The effect of unbalanced force perpendicular to the line of stroke, it may produce the variation in the pressure on the rails, which results in hammering action on the rail. So perpendicularly may cause hammering. Along the line of stroke cause variation in tractive force and swaying couple. So with the maximum magnitude of this unbalanced force along the perpendicular to the line of stroke is known as hammer blow, called hammer blow. So we can remember the how the hammering will be done. So if a man is operating the hammer which is to be operated perpendicular to the existing one, so that is the remembering. So and what are the effects of unbalanced primary force for during the variation in tractive force and swaying couple, that we will discuss now. So what is the tractive force and what is the swaying couple? The resultant balanced force due to two cylinders along the line of stroke is known as tractive force. Let us consider a crank for the first cylinder to be, if you see in the diagram, so let us consider the crank for the first cylinder to be inclined at an angle of theta with the line of stroke. So if you see with an angle of theta, if you see in the diagram, that is the crank making an angle of theta degrees with the line of stroke, which was mentioned in a pink color. Okay. Since the crank for the second cylinder is at a right angle to the first cylinder, therefore the angle of inclination for the second crank will be actually one crank and the second crank, these two are mutually perpendicular. So if the first crank is making theta with respect to line of stroke, then how much of second will be means already it is existing with 90 all, and the first thing is with theta. So totally it is 90 plus theta degrees. Let us consider m be the mass of the reciprocating parts per cylinder and c is the fraction of reciprocating parts to be balanced. We know that the unbalanced force along the line of stroke for the cylinder 1. So we know the formula. What is that? Unbalanced force along the line of stroke, that is 1 minus c into m omega square r cos theta. And what about the cylinder 2? Same 1 minus c into m omega square r cos for cylinder 2 is existing at 90 plus theta angle. So here 90 plus theta. As per the definition that the tractive force is Ft, tractive force. The resultant unbalanced force along the line of stroke is given by the both. So the tractive force is due to the two cylinders. So commonly write it with adding this 1 minus c into m omega square r cos theta plus 1 minus c into m omega square r cos theta plus 90 plus theta. So finally what we are getting here 90 plus theta. What does it mean? Cos 90 plus theta, that is minus sin theta. So 1 minus c into m omega square r into cos theta minus sin theta. That is the resultant. The tractive force is maximum or minimum depending on the theta value. So here where is the theta? Cos theta minus sin theta, which is to be maximum or minimum. Suppose let us consider if cos theta minus sin theta is maximum or minimum, so we have to differentiate this and equate to 0. D by d theta of cos theta minus sin theta is equals to 0, or cos d by d theta of differentiation of cos minus sin minus differentiation of sin is a simply cos. So minus sin theta equal to cos theta. So finally tan theta is equals to minus 1. Whatever the inverse of tan theta is equals to 135 degrees or 315 degrees. Okay, it is easier to remember. Thus the tractive force is maximum or minimum when theta is equals to 135 degrees or 315 degrees. So find out, substitute this there and finding the values. So maximum and minimum values of tractive force for the variation in the is plus or minus 1 minus c into m omega square r into cos cos 135 degrees minus sin 135 degrees. So either we can substitute 315 simply, we can get the positive, or theta is equals to 135, we can get it the negative. So finally we are concluding this with plus or minus root 2 into 1 minus c into m omega square r. So this is the formula for tractive force. With the variation in tractive force is how much of variation? Plus or minus root 2 into 1 minus c into m omega square r. This is the final formula what we have received. This With this, the tractive force was completed. Whatever the another force, another unbalanced force is creating along the line of stroke, that is swaying couple. The unbalanced force along the line of stroke for two cylinders will constitute a couple about the central line YY. So these about the YY, these two create a swaying couple. This swaying couple will affect about the vertical axis and tends to sway the engine alternatively in clockwise and anti-clockwise direction. Hence this couple is known as a swaying couple. For 2 marks he may ask tractive force and swaying couple, and one more thing is hammer blow. These three are very important for the 2 marks. Let A be the distance between the central line of the two cylinders. Here also make a note x y be the reference or along the line of stroke, and above that and below that two engines or two cylinders are placed. These two are separated by a distance small a, and swaying couple is given by 1 minus c into m omega square r cos theta into a by 2. Since from the reference of the pink, that is a reference line only, the swaying couple is about vertical axis. So a by 2. And here also a by 2, which is at the exact middle. Then minus into 1 minus c into m omega square r cos of 90 plus theta into a by 2. So finally what we have received here? 1 minus c into m omega square r into a by 2 cos theta plus sin theta. Here also once again the swaying couple is maximum or minimum when the cos theta plus sin theta is maximum or minimum. So finally for cos theta plus sin theta to be maximum or minimum, we have to equate it to 0. So differentiating with theta and equate it to 0. So finally, what is the angles we have received here? Theta is equals to, same method we have followed, applied on the tractive force also. So theta is equals to 45 or theta is equals to 225. Then substitute this with the the original equation, that is plus or minus 1 minus c into m omega square r into a by 2 cos 45 degrees plus cos sin 45 degrees, both are same. So at the rate of plus or minus a by root 2 into 1 minus c into m omega square. If you see the tractive force equation, that is plus or minus root 2 into 1 minus c m omega square r. Here plus or minus, if you place the a aside, 1 minus c into m omega square r. Here, in order to take up these values, there is a slight variation. For tractive force, the root 2 is placed, or root 2 is multiplied with 1 minus c into m omega square r. But in the swaying couple, it is divisible by root 2. Okay. In order to reduce the magnitudes of a swaying couple, the revolving masses are introduced. But the revolving masses causes the unbalanced force to act at right angles to the line of stroke. These forces may vary the downward pressure of the wheels on the rails and may causes the oscillation of the locomotive in an vertical plane about the horizontal axis. Since the swaying couple is more harmful than a oscillating couple, therefore the value of C from 2 by 3 to 3 by 4 in two cylinder locomotives with the two pairs of coupled wheels. In the larger four cylinder locomotives with three or more pairs of coupled wheels, C is taken as 2 by 5. So, moreoverly, the coupled force is more harmful, swaying coupled force is very harmful than tractive force. Then the harmful hammer blow. We know that the maximum magnitude of unbalanced force along the perpendicular to the line of stroke is known as a hammered blow. We know that unbalanced force along the perpendicular to the line of stroke due to the balanced mass capital B at a radius small b, in order to balance the reciprocating parts only, that is given by b omega square b sin theta. This force will be maximum when theta is unity, that is theta is equals to sine. When will be the sine is unity? 1, that is theta is 90 or 270 degrees. Therefore the hammer blow equation is b omega square b. This is the maximum. The effect of hammer blow is to cause the variation in the pressure between the wheel and the rail. If you see in the diagram, for one rail and one revolution of the wheel, P be the downward force, downward pressure on the rail, and net pressure between the wheel and the rail will be P plus or minus B omega square B. In addition to that, we are adding the pressure, down pressure. If P minus B omega square B is negative, then the wheel will be lifted from the rail, and therefore the limiting condition in order to wheel doesn't lift from the rails is given by P equal to B omega square B, and the permissible value of the angular speed omega is equals to square root of P by BB. This is the equation for the hammer blow. What is the final hammer blow equation? Is B omega square B, and the permissible pressure or net pressure is adding between the wheel and the rail, then P is given by B omega square B. So with that we constitute the relation between the uh, partial balancing of locomotives, and then these partial balancing of locomotives, how they classified singular or inside and outside, and after that single are uncoupled and coupled. After that, due to the line of stroke balancing, along the line of stroke balancing we are getting two faults, that is tractive force and swaying couple. And due to the unbalanced force along the perpendicular to the line of stroke, that is hammer blow. So with that we are concluding the equations to find up the this hammer blow and swaying couple and tractive force. Okay, in the next class we will solve some of the problems based on these contents.